Good morning, everyone, and thanks for being here. And we'll get Juan on when we get to that portion of the presentation. Before we get started, I want to go over a few logistics. Today's webinar is based on two GPG assessments, the variable speed magnetic bearing or maglev chiller and the variable speed screw chiller. And both the full reports as well as summary findings and infographics are available on gsa.gov. And today's webinar is one of a series. Our February webinar will be on plug load control, and it will discuss findings from GPG's report on advanced power strips, as well as more recent developments in the field of advanced power strips and smart outlets. In March, we'll be featuring the Honeycomb Solar Thermal Collector, and this solar thermal collector is particularly effective for solar hot water systems without a storage tank. April's webinar will discuss electrochromic windows. In December, GPG released two reports of test bed assessments of electrochromic windows in general office space and highlighting the effectiveness of these windows in glass curtain wall facades. Recordings of the webinars as well as an upcoming schedule is available at gsa.gov/GPG. Today's webinar, as some of you have experienced, participants are muted and you'll be in listen-only mode. But you can submit questions using the chat box on the right side of your screen. And you don't need to wait until the Q&A session. That'll happen at the very end of the presentations. In fact, we encourage you to submit questions throughout the presentation. And now Mike Lowell, who's the GPG project manager for the variable speed screw chiller assessment, will be facilitating today's webinar and walking through the agenda. Mike?
Thank you, Andrea. Next slide. Here's the agenda for today's webinar, which will include a brief overview of GPG by the Director of the Program, Kevin Powell. After Kevin's opening remarks, we will transition to the technical portion of the webinar. With that, Kevin, welcome. Next slide.
Yes, next slide. Thank you very much. And yes, there I am crabbing. Okay, next slide. Just a couple of notes about what the aims of the emerging technology programs at GSA are, and then how this particular research supports that. There are two programs that constitute the Emerging Technologies Division at GSA. The first is the Proving Ground, and this is a result of, we're actually presenting results of a couple of field trials from Proving Ground projects. And then the intent of these Proving Ground projects is to provide real-world data that validates the performance promising technologies that do prove out, and you'll hear about two that have proved out, are ones that we then are looking to further deploy across our portfolio in order to improve its financial and environmental performance. So, next slide. Next slide. Yeah, there we are. So I think the key thing, and what I hope everybody will understand on this call, is that there really is a lot of investment in really developing next generation building technologies. The challenge for most of those technologies is that in the real world operating environment of buildings, there's a fundamentally conservative impulse to replace things with the same things because you know they work. The point of the Proving Ground program is to take out some of the risk of essentially the next generation technology because there's some concern, does it actually deliver in the real world? And you know, our experience is sometimes it does with certain kinds of caveats, and sometimes it's really just simply not ready for prime time. So that's what we try to do. We try to bridge that, as it shows on the slide, the technology valley of death. And the important thing to understand is that these results have enabled GSA to make investments in our buildings, even in these fiscally constrained times, that are really delivering real-world savings. So next slide. Our process is that every year we hold we publish a request for information that actually that closed in December. The current one, that is to say, after we receive all of our submissions, we have independent subject matter experts score them. We select a series of semifinalists, hear from those semifinalists, select the best of the best, pilot those within our portfolio, partner with Department of Energy National Labs, who really are world-renowned experts in conducting these kinds of field studies, see how they shake out, and then those that actually deliver promising results, we recommend those for deployment across our portfolio, and also come up with kind of guidance that can help. I should also say that the results from proving ground evaluations are intended to also facilitate adoption by private sector folks. So that and we've actually found that there's a fair amount of confidence that these outcomes generate in the private sector for exactly in the same way that they do for us. Next slide. And with that, I'm going to turn this over to Jeremy Jenks of Pacific Northwest National Lab.
All righty. Thank you, Kevin. Yeah, I actually operate in that Valley of Death region, working on thermally driven heat and power cycles, cooling cycles. So a lot of experience in that realm based off that slide you showed earlier, Kevin. Next slide, please. So I'm going to present some results from a study that was conducted by staff here at PNL on a variable speed magnetic bearing chiller that was installed side by side with a different unit we'll talk about at a federal building and courthouse located in Pine Bluffs, Arkansas. Next slide, please. So in general, just the big picture, 10%, roughly 10% of the energy in offices goes to space cooling. And of that 10%, 32% of the commercial buildings are actually relying on chillers to provide that space cooling. Next slide, please. So GSA is unique in that 80% of their floor space is attributed to large buildings. And most of those buildings are cooled with water-cooled chillers. So looking into applications or opportunities to reduce the power requirement for a given cooling load is certainly an advantage for GSA. Next slide, please. This is a cutaway view of a variable speed magnetic bearing chiller. You can kind of look at all the different internal working parts there. But speaking in general, the compressor uses 2 impellers on a single high-speed rotating shaft, which is actually the only moving part in the compressor. And the 2 impellers provide 2 stages of compression, which provides high efficiency in a fairly compact design. The compressor has a fully integrated variable speed drive, and this allows the compressor to be highly efficient, certainly relatively efficient compared to the other chiller we'll talk about in a minute, especially at partial load. That's one of the unique things with this particular compressor. The shaft with impellers is levitated during rotation using digitally controlled magnetic bearings, and that unique feature reduces the friction and heat caused by conventional bearings, adding again to the efficiency, but it also eliminates the need for lubricating oil and the ancillary equipment that go into that lubricating oil system, which reduces the amount of overall maintenance requirements. So again, yeah, the compressor is digitally controlled with microprocessors that manage the compressor operation and provide self-diagnostics and correction. So in a nutshell, that is the magnetic bearing compressor that you see right there. Okay, next slide, please. So this study was conducted during a fairly long cooling season back in 2012. The study period was started earlier than anticipated. I believe it was in March and went on through to September. So it gave the researchers a good opportunity to look at a lot of different data. This particular building is over 100,000 square foot, and it has two chillers located, two 150-ton chillers located in the mechanical room. So what occurred is one of the chillers was due to be replaced. It was a rotary screw chiller, and it was replaced with this magnetic bearing chiller that you can see detailed on the image on the right, called variable speed chiller 1. And so both units were instrumented to determine the overall coefficient of performance and look at that throughout the entire cooling season. Next slide, please. So this other chiller was a rotary screw chiller that was working side by side with the new magnetic bearing chiller. It's a 150-ton rotary screw chiller that was installed in 1993, and it really was before there was any variable speed. It was installed before there was any variable speed chillers, and these smaller chillers, I think more from a cost perspective than anything else, needed to be rotary screw at anything below, I think, anything below 200 or 300 tons. The centrifugal chillers just really didn't exist. One thing to note is this is a side-by-side study, but the refrigerants that were used were different. So the the rotary screw chiller was using R22 refrigerant, and the magnetic bearing chiller was using R134A. Now, if you just do a quick look at those two refrigerants at standard state points for HVAC, you'll find that, at least from my back-of-the-envelope calcs, the rotary screw compressor, well, the magnetic bearing chiller is actually having to do about 4% more work than if you were to put in R22. So this, in that sense, this study is somewhat conservative in the charts that are following. If you look at the table on the right, these are just comparing the two chillers. The original chiller, they're both 150 tons. The only difference here is the new chiller obviously has the magnetic bearing, and there are two individual compressors in that particular unit. The biggest thing that you can look at, the oil tank heater, there was one of those for the original chiller, not applicable for the new chiller because it doesn't require oil. And then you can see the difference in refrigerant there, and at the bottom, of course, oil is not applicable for the new chiller. Next slide, please. This is showing that the overall coefficient of performance versus the chiller load for both of these units. The gray line is showing the old chiller performance, the rotary screw chiller, and then the green is showing the new chiller. And it's really just a lot of data that's kind of hard, it may be difficult to see a trend, but what you can see looking at the green data for the new chiller is that there's an optimal operating point when the compressor RPMs are slowed down, the compressor speed is slowed down, and that occurs between 27 and 33% of full load. So we're actually seeing by using this variable speed and increasing efficiency. And given that most of the time the chiller is going to be operating at part load, that's a huge benefit for this type of chiller. As for the old chiller, you can see it drops off as you reduce the cooling load. And the reason for that is these old chillers that didn't have variable speeds had to restrict the refrigerant flow in some manner. And of course, there's essentially an associated loss of work, usable work associated with that, that reduces the overall coefficient of performance. And the coefficient of performance, for those of you that may not be familiar, is not an efficiency. It's just a measure of how much power or how much cooling we can get out of this unit versus how much power we have to put into it. In general, 42%, what we found was 42% energy savings because of this reduction, this increase in coefficient performance as we reduce the load. There's a 42% energy savings from comparing one chiller versus the other chiller. Okay, next slide, please. At the end of the study period, there was a roughly a $9,000 energy cost reduction per year, assuming the energy or the cost of electricity shown there in the subtitle. From a lot of studies that P&L had conducted previously for a Navy program tech valve, the payback period is strongly dependent on the installation costs, but in general, throughout most of those studies, it was found to be less than 5 years for this particular technology. Next slide, please. Operation and maintenance, I spoke to this a little bit earlier, but clearly some of the benefits, it's smaller and lighter than similar capacity compressors. It's quiet because of the magnetic bearings, it's frictionless. So it can be placed, especially for new spaces, these chillers can be placed next to occupant spaces. And of course, as we saw, it's more efficient cooling at you get more efficient cooling at lower partial loads as you reduce the speed of these centrifugal chillers. Next slide. All right, I'll hand it off to Juan I don't know if he's available or not.
Yes.
Andrea?
And Juan Grego is a regional energy engineer for GSA Region 7, and he's now going to provide insights to the region's MBC deployment and operations. Thanks, Juan. Take it over.
Thank you, Kevin. Thank you, Mike. Good morning, everyone. It's an honor for me to be here and talking about our experiences with the deployment and operations of these mag-bearing chillers. Next slide. Since the release of the GPG report on the mag-bearing chiller technology, GSA has seen an uptick in the deployment of the mag-bearing chiller technology. Overall, GSA has deployed 210 of these mag-bearing chillers. Region 7, as a region, we have installed 68 of them with 4 pending. Next slide. So the 68 mag-bearing chillers represent a little more than a third of our Region 7 chiller inventory. The range of sizes of our mag-bearing chillers range from 60-ton 1 compressor to 750-ton 4 compressor units. About 90% of these mag-bearing chillers are water-cooled, with the remaining being air-cooled. Now, what makes the mag-bearing chillers attractive is their low IPLV values, which are in kilowatts per ton. As you can see, the mag-bearing chillers, the values for these mag-bearing chillers range from 0.3 to 0.35, which are lower in comparison to what you see for rotary screw or centrifugal chillers. Little explanation on the IPLV. IPLV stands for integrated part load value. It measures the overall average efficiency of a chilled cooling system. So basically, in a nutshell, the lower the IPLV value, the more efficient your chiller. Next slide, please. Next slide. Okay.
I have swapped. You should see it now. There might have been a little delay.
No, thank you so much.
Thank you, Juan.
No problem. Lessons learned from the incorporation of these mag bearing chillers. These mag bearing chillers need to be operated differently since with this technology, you maximize your energy efficiency at lower partial loads, which means that a few things. One, that the O&M contractor needs to be properly trained to operate and maintain these chillers. And so we've incorporated that requirement in our scopes of work when we conduct these chiller replacement projects. The other thing that we have learned from going through these chiller replacement projects is that because of the energy savings of going with these mag bearing chillers, that depending on the territory in which you're replacing these chillers, that whether it's within Encore or Center Point or Energy or whichever area, in most cases, these chiller replacement projects are incentive eligible. So basically, they're driven off of lower IPLV values when you're replacing a chiller with a mag bearing chiller, and as I've already shown, the IPLV values are lower for mag bearing chillers as compared to rotary, screw, or centrifugal chillers. And another requirement is that they have to be AHRI certified. Give you a quick example. We were in the process of receiving incentive money from Entergy, where we had a $600,000 project where we had incorporated mag bearing chillers over at both the Abear and Hale Boggs federal facilities down in New Orleans. It was a $600,000 project, and we're in the process of receiving $60,000 in incentive money from Entergy. So this helps for two reasons. One, receiving the incentive money helps in terms of shortening your payback, and then secondly, we can deposit the $60,000 into, which we normally do when we receive incentives, toward BA63 money, which we then use toward future energy projects. So it's sort of a win-win, for GSA there. Unfortunately, it took us a while to understand that that there are incentive programs out there for chiller replacements. But we are getting up to speed on that requirement. Next slide, please. And actually, the last two slides are going to be case studies. This one involves the Fort Worth Federal Center, Building 23. Back in April of 2015, we had replaced two chillers with mag bearing chillers, both water cooled, 150 ton, two compressor. Now the training data that you see represents the month-by-month electrical consumption for the entire complex, not for the equipment. Nevertheless, as you can see, since we installed these mag bearing chillers, that we saw almost a 30% drop in our electrical consumption in FY16 from FY15, which equated to a reduction of almost 2 million kilowatt hours. We also saw an electrical utility reduction of $126,000, or about a 28% cost reduction, partially due to the mag bearing chiller technology. This was the best case scenario. The next slide will show the worst case scenario. This was the Pickle Thornberry complex in Austin, Texas. where the project was handled at the service center level. They had replaced a 600-ton train chiller with a 440-ton mag bearing chiller installed back in December of 2013 with little or no input from our regional headquarters. And as you can see, we actually saw, in many cases, an actual slight increase in our electrical consumption. And when I later took part in an internal audit for the Austin Service Center back in 2015, when we spoke with the O&M contractor, we found out that the O&M contractor was actually operating these mag bearing chillers on full load, just as if they were operating a centrifugal or screw chiller. And so they weren't provided the training on how to properly operate these mag bearing chillers, and so we had to make arrangements for that training to occur. And so those are the two takeaways from this particular case study for Prickle Thornberry. I think that is it on my end. I think I'm going to pass it on to Michael for our next presenter. Thank you.
Thank you, Ron. Next, we have Dan Howett. Dan is an R&D staff member at Oak Ridge National Laboratory. His focus is on emerging technologies that serve commercial and industrial facilities, and Dan is the primary investigator for the variable speed screw chiller. Dan, it's up to you.
Okay, well, good morning, everybody. Next slide, please. This evaluation occurred at the Sidney Yates building in Washington, D.C. in 2015 and 16. The building had recently been renovated, and the chiller plant was about to undergo a major overhaul, replacing two older centrifugal chillers. As part of this overhaul, GSA chose to install a 275-ton variable speed screw chiller in parallel with a 275-ton magnetic bearing centrifugal chiller. The magnetic bearing chiller is of the same type evaluated in the previous GSA study and is widely accepted by the agency. Both units will be connected to the same chilled water and condenser water loops. This configuration allowed GSA to evaluate their performance under near identical operating conditions. Next slide, please. The original report from this evaluation was issued in December 2016. In February 2017, the manufacturer of the magnetic bearing chiller, Daikin, and the compressor, Danfoss, raised concerns about aspects of the report. As a research organization, Oak Ridge National Lab welcomes fair scrutiny, and GSA withdrew the report and commissioned additional internal and third-party reviews. After 6 months of review, 3 major points emerged. Number 1, the report's substance and overall conclusions are unchanged. Number 2, language within the report was edited to clarify points that had been misinterpreted. Also, documentation has been added to better characterize the study as a whole. Number 3, at the suggestion of the National Renewable Energy Laboratory, the third-party reviewer, chiller performance data was analyzed with a second method commonly used in energy savings performance contracts. This alternative analysis corroborated the report's initial findings. Details of the review process are captured in a 14-page preface that was added to the reissued report. Overall, the report grew from 32 to 66 pages with the added documentation. Next slide, please. There are 2 key design features which distinguish the variable speed screw chiller. First, the compressors are of a positive displacement design. This allows the unit to rapidly respond to the changing cooling requirements found in real buildings. Second, cooling capacity is controlled by simply changing the motor speed. These 2 features eliminate the requirement for mechanical unloaders found on centrifugal compressors and older rotary screw machines. Without those unloaders, their inherent inefficiencies have been removed from the refrigeration cycle, thereby increasing the chiller's performance in the dynamic world of actual buildings. Next slide, please. Here are pictures of the 2 machines in the mechanical room of the Yates building. They were connected in parallel to the same chilled and condenser water loops. During the test, the maintenance staff operated the units on a day-on, day-off schedule for the most part. The team kept track of the condenser water temperatures and percent full load such that, as much as possible under field conditions, the unit spent the same amount of time under the same conditions. Next slide, please. Instantaneous data was collected in 5-minute intervals. The key performance parameters were the energy consumption rate, measured in kilowatts per ton, and the percent full load at which the chiller was operating. The team chose to measure performance instantaneously as opposed to averaging over a 5-minute interval, so we could truly capture how performance varied under dynamic field conditions. Using average 5-minute values would have resulted in smoother curves rather than the broader scatter plots, but the performance variance would have been lost. With each chiller's data set, a second-order polynomial was curve fit to the data. These curves are shown on the graph. I would like to clarify a point of possible confusion between this graph and the graph shown in the previous evaluation of the magnetic bearing chiller. In the previous study, the chiller's performance curve rose as it went into a part load condition, whereas in this study, the curve lowers as load decreases. This is because the previous graph measured the coefficient of performance, in which a high curve indicates better performance. The graph in this study measures the energy consumption rate in kilowatts per ton, in which better performance is shown by a lower curve. It's the same outcome shown using two different metrics. A weighted average was applied to the curves in order to compare each unit's performance. At the Yates building, the variable speed screw chiller's energy consumption rate was 11% lower than the magnetic bearing chiller. It must be noted that performance at other sites under other conditions can vary. Therefore, the report's final recommendation is that both chiller types can show comparable energy usage and should be considered by facility owners. Next slide, please. As mentioned earlier, the National Renewable Energy Laboratory recommended that the data be parsed in a second method, in which the energy consumed by each chiller in a given hour was compared to the average outside air temperature during that hour. This method is used in energy savings performance contracts when the contractor wants to compare the performance of two chillers before and after a retrofit. These graphs capture that data and further separate them based upon the condenser entering water temperature. They show that across the unit's operating spectrum, the variable speed screw chiller consumed less electricity than the magnetic variant chiller. The exception is at the right of these graphs when the outside air temperature and condenser entering water temperature were both warmer. At this point, the magnetic bearing chiller started consuming less energy than the variable speed screw unit. Overall, the average energy consumption indicated by this analysis method corroborated findings from the previous slide. Next slide, please. One performance claim from the variable speed screw vendor is that their design could easily handle swings in condenser water temperature that were outside the design parameters. At the Yates building, design temperatures were 65 to 85 degrees Fahrenheit for both chillers. In March of 2016, there was a stretch of sunny, warm days when air conditioning was required, but the cooling tower basin was at 55 degrees Fahrenheit. The variable speed screw chiller handled the startup without any issues. When the magnetic bearing chiller vendor was contacted, they recommended not starting the unit until the condenser water loop had reached 65 degrees Fahrenheit. This cold water condition could occur at other sites during shoulder months or during a time when a tower's basin heater failed. During a hot spell in the summer of 2016, we had the opportunity to test the opposite condition. The operating staff allowed the condenser entering water temperature to rise to 95 degrees Fahrenheit. This test replicated the condition that might be found if a cooling tower fan were to fail, or if a multi-cell cooling tower were to completely lose one or more cells due to maintenance or other conditions. The magnetic bearing chiller tripped off at its preset high limit. The variable speed screw unit operating continuously up to 95 degrees Fahrenheit without any issues. As part of discussions with the magnetic bearing chiller vendors, they stated that their units could be built to handle any condenser water range found at a site. The operating parameters would simply have to be stated up front in the specification. Next slide, please. Historically, screw chillers have a reputation for being too loud. My old boss from the early 90s refused to specify screw units for that very reason. Below is the manufacturer-provided data that shows the sound levels across each unit's range of operation. As you can see, they are very similar and you've already heard testimony about the quietness of the magnetic bearing chiller. Though the Yates building mechanical room did not allow for acoustic testing, I can tell you anecdotally that it was very easy to carry on a conversation in the room, even near the chillers. The noisiest part of the room was near the pump batteries. Next slide, please. This slide shows some direct comparisons from the manufacturer's literature. The variable speed screw chiller has one 275-ton compressor. The magnetic bearing chiller is built on a 400-ton frame and has two 200-ton compressors, even though the specified cooling capacity for both units was 275 tons. During the evaluation, the Oak Ridge and GSA team had extensive email conversations with the equipment rep near Washington, D.C., who was supplying the magnetic bearing chiller. The 400-ton frame was questioned, but the rep repeatedly stated that the configuration was selected as it was, quote, the most efficient to meet the 275-ton requirements. The complete email chain is included in the final report. The two chillers have similar external dimensions, while the variable speed screw unit is heavier. The variable speed screw vendor gave a budget price of $119,000 for their chiller, while the MBC unit was purchased for $185,000 through normal GSA procurement channels. Both prices included similar packages of startup support. The budget price for the variable speed screw unit seemed unusually low, so a third party was used to go shop the vendor. The price was confirmed through this process. Next slide, please. This test, plus the previous one which focused on the magnetic bearing chiller, indicate that both technologies offer performance that is substantially better than a standard water-cooled chiller as defined by the Federal Energy Management Program. A facility's HVAC needs will best be served if facility management and the design team consider both chillers when looking at purchasing new water-cooled units. The needs of a specific site must be weighed against traits of individual chillers. Next slide, please.
Next, we had feedback from the facility operation team at the Yates building. We'll be receiving feedback from Kenny Thompson, who's the GSA property manager, and as you can tell by the hat in the photo, a rabid Dallas Cowboys fan. And serving with him are Glenn Stewart and Randy Burgess of TELRR Joint Venture, the Yates Building O&M contractor. Kenny, I'll let you and the team take it over.
Good afternoon, everybody. Just wanted to give a couple of things. We both had the Daikin and the Carrier chillers, and I think they both work great. But I'm going to turn it over to the two experts, Randy and Glenn, who deal with them on a daily basis. Hello, Glenn.
Yes. Hello, everybody. This is Glenn Stewart.
And next slide, Andrea.
Yes, this is Glenn Stewart and Randy Burgess. The VFS runs more in season, and it does accept lower temperatures. When we ran the Carrier would start at about 50 degrees, but the Daikin would not start under 65 degrees. And after hearing from Daikin, they were saying that they can build that differently for different areas. And that being said, as you see in the picture, the cooling tower basin is about 25 to 30 feet in the ground with no heaters. So we have no way of heating up our condenser water during startup on cool mornings. So different setups may lend better for the Daikin than our setup, I guess is what I would say to that. I would say that the Carrier chiller is a little noisier at low loads. It tends to surge a little bit, but both chillers are very good with their noise levels. So I would say that both chillers have their positives and they have their challenges too. Do we have another slide here or? Yeah. So here's where it shows how you go down into the sump of the cooling tower. So a little different. I don't know if anybody else would see that out there except for what we have here. And yeah, the screens that you see are actually the intake for the air, and then where you saw on the top of the brick towers, that's where the outlet is. And the hole is how you access to go down to clean it or
check the pumps or something of that nature. So, but in the end, we give both chillers a thumbs up in our actual daily work with both of them. And just to add on that we have Carrier actually takes care of our Carrier chiller, and Daikin takes care of our Daikin chiller, and both of them have given us excellent service, and we plan on using both of them in the future. Do you have anything?
No, I think you did great.
Okay, thanks, guys. And next we'll have Dan Howard, who will talk about best practices. Dan?
Well, welcome back. We're going to go through a few thoughts that should be considered when looking at a new chiller. In both evaluations of the magnetic bearing and the variable speed screw chiller, focus was entirely on the chiller. That piece of equipment is but one of several that make up a chilled water system. There are pumps, cooling towers, a piping system, and controls that oversee everything. Perhaps circumstances are such that a heat exchanger can be added to allow pre-cooling. Also, in September 2016, the GSA Proving Ground published an evaluation of a chiller control optimization system that might be right for your site. It is important that a qualified mechanical engineer do a thorough technical and economic analysis to determine the right combination of equipment and controls to serve your facility. And as the system is being installed, perform proper commissioning to make sure all equipment is working correctly in concert with each other. As for peak cooling loads, the H project had an odd twist that deserves mention. The original chillers at the site were two 350-ton centrifugal units. Reflexively, the design team was steering towards installing units of similar capacity. Only after performing a heat gain loss calculation did they learn that the building use had changed such that 275-ton units would be much more appropriate. Next slide, please. Okay, oh yeah, that is the correct one. As mentioned earlier, the magnetic bearing chiller was more sensitive to condenser water supply temperatures. You know what? I'm missing a slide here.
Should be the load profile.
Yeah, I see. The mistake that's been made. The key point to make here is that as you're working with as you're looking at your building, pay attention to the profile that that building operates at. As you can see, and this data below comes straight from manufacturer provided data. As you can see, as the load profile changes, the kilowatts per ton for each type of unit will shift, whereas at 100% load, the variable speed screw unit has a slightly higher kilowatt per ton rating, where down at 50% load, it starts to go a little bit lower. If you have a building that operates consistently at a very high load rate, such as perhaps a data center, that could skew your results one way or another. Or if you have a building that operates a lot across a wide spectrum with a large amount of time at low load or mid loads, that could skew your decision in another direction. It's important to pay attention to your load profile when selecting a chiller. Next slide, please. As mentioned earlier, the magnetic bearing chiller was more sensitive to condenser water supply temperatures that were outside its design operating range. If you have a site that is likely to experience wide swings in condenser water temperature, or one where a chiller trip would be costly, such as a data center, be sure to clearly specify the full range of temperatures that the chiller might experience at your site. The evaluation at the Yates building did not measure any marginal costs that might be associated with a magnetic bearing chiller with a wide range of condenser temperatures, but these must be evaluated, specified, and balanced with the site's actual requirements. Next slide, please. In areas which have unusually high electric demand charges, it might be viable to install a thermal storage system or some other method of shifting the peak demand to off hours. And finally, all chillers need maintenance. Different manufacturers have different maintenance presences in various parts of the country. The same can be said for the various O&M contractors who operate facilities. Their comfort level with different chiller brands and technologies can vary. Make sure that you'll have access to maintenance resources when selecting your brand of chiller. Mike, that wraps up my portion. Back to you.
Thanks, Dan. And now we'll enter into our Q&A. Thank you. Let me switch screens here. And let's see. First off, Zach asked if continuing education credits would be offered for this training, and the answer is yes. You need to complete a survey to receive the credit, and you can reach out to Michael Hobson of GSA. Let's see. Scott Chalmers asked the question, I think, JJ, this will be for you. Aren't there also accelerometers and capacitors for the MBC chiller as well? JJ, is that the case?
Yeah, I'm not sure on that one. I'd have to look into the technical drawings and see where those would be located. I wouldn't be surprised.
Okay. And then, JJ, would you have any ideas to the required maintenance for the MBC?
Yeah, I think there's another question coming up on that that I think Juan might answer, but in general, I'm not sure exactly what the manufacturer requires, but as we talked about earlier, the variable speed oil free centrifugal chiller with the magnetic bearings may result in lower maintenance costs as a result of elimination of the compressor's oil system. We didn't look at actual requirements.
Okay, thanks. And let's see here. Scott asked, what is the turn down on the maglev? Quote unquote, he says, I have heard 10%. I see JJ doesn't know. If someone else knows, please let us know and chat the answer, and we'll try to pick that up. I think the answer, the cost answer was covered. Someone asked a question about the cost between the two, and that was answered in Dan's presentation. And then Dave asked, how do the paybacks for the MBC and DSS compare to payback compared to a modern centrifugal? Dan or JJ, I don't know if you have any thoughts on that.
Yeah, Mike, this is Dan. When looking at the payback for these chillers, there are so many factors that go into calculating the payback: your utility rates, your operating profile, how many hours per year do you operate. That is so heavily dependent on individual site data that to try to give a, chiller A has a, 3-year simple payback compared to chiller B, anything that I would say to that effect would not be valid at any given site. So it's, to get back to one of the points that was made near the end of the presentation, each site has to really be scrutinized based on its own individual characteristics.
Okay, thanks. And Keith asked, is the noise of the MBC in the higher or lower octave band? And as Dan's presentation showed, both chillers, the MBC and the DSS, operated in that 70 to 80 decibel range. Keith also asked, what kind of compressor warranty does the manufacturer provide? And JJ didn't have any idea. I don't know, Juan, if you have an answer to that by chance, given your proliferation of MBCs in your region?
Yes, I don't have. I honestly don't have that information offhand, but I can research that and provide that.
Okay, thanks.
Yeah, no problem.
Hey, Mike, this is Dan.
Yes.
I had a comment on the issue of manufacturer's warranty. Prior to joining the lab, I spent about 10 years as a specifying design engineer. In my experience, if a buyer wants a certain warranty, a certain period, manufacturers are open to negotiating those. Again, site by site, based on what the buyer wants, what would be in their best interest, talk to each manufacturer and figure out what would best serve the individual site's needs.
Okay, thanks. Bob asked, do they have chillers that are external style air-cooled? JJ, I see you answered in the chat, but why don't you go ahead and take that for the rest of us?
Yeah, I was just looking online, and yeah, they do have direct air cooled chillers for, I guess, Is he speaking about MBCs?
He doesn't say, but I'm going to say MBC.
If it's for MBCs, the answer is yes, they do.
Yes. As a matter of fact, I think as Juan mentioned, Region 7 has several air-cooled MBC chillers. Tim asks, how many manufacturers offer the MBCs, and do all major manufacturers offer them? And JJ, I'll let you weigh in just a second, but Juan, again, they've got over 60 of these chillers in their region. He said he didn't know offhand how many manufacturers offered the MBCs, but they've installed MBC chillers from Smart, York, Multistack, Arctic Cool, and Daikin in Region 7. JJ, I don't know if you're aware of any other additional manufacturers.
Oh, Mike.
Go ahead.
No, go ahead.
I was just going to say, just doing a cursory look online, there's a lot of chillers out there that offer MBC. I don't know the exact number.
Okay, thanks.
Mike, Mike, I wanted to follow up that you asked as far as warranties on the compressors for mag-bearing chillers. It looks like it's a 5-year warranty. So what we asked normally would be a 1-year warranty on workmanship and materials plus an extended 4-year warranty on compressor parts and labor.
Okay, thanks. And then I think this next question might be for you as well, Juan. You might not know, but David asks, regarding the incentive, do you know of an expiration date for the incentive? And then you may want to qualify. I think the utilities that you were talking about, of course, are somewhat unique to Region 7. So,
well, there is an expiration date as to when we complete projects. Like we have to submit the paperwork to the broker, and then typically when we perform these projects, after they accept our applications, they have to verify the energy savings. Basically, there's a pre-inspection and there's a post-inspection. And they usually do provide a deadline on when we have to complete the project. Oftentimes, it's usually toward the end of the calendar year, usually toward the end of November. There are some brokers where, let's say we aren't able to complete the project, they'll carry it over to the next year for the incentive. Now there's also a deadline on when we submit applications. We unfortunately we were trying to submit. I guess we were trying to submit an application for an exterior light barge. Obviously, it's different from mag bearing chillers, but they had a deadline on submitting the application. We got in too late. The money had already been exhausted, and so our project was not considered. And we couldn't hold up the project for next year because the project was ongoing, and so we had to move forward. So I hope that answers your question.
Yes, thanks. And then I think next question is for you as well, Juan. Matt asked for the whole building energy use consumption. I believe this is the two graphs you had in your presentation. The whole building energy use comparison with those graphs, weather normalized.
That's a good question. I don't know offhand if they are. I can look through that and get back to you on it.
Okay, thanks. And then both Doug and Gary asked if at the Thornberry if there was improvement after training. I noticed in the chat that you said that you don't have post-training performance data, so we don't know yet.
No, but we can compile the data and provide and get that out to the guys. So yes, we don't have it, but we can compile it.
And then Brian Singleton asks if the chillers meet the P100 requirements, and they do. Let's see. Scott chimes in on the maintenance of the MBC chillers, that they require quarterly maintenance to check accelerometers and capacitors. So thanks, Scott. And then he also says that the cost overall for that maintenance is not that much difference compared to an annual on the centrifugal chillers. Let's see. What else here? Kinshram, just kind of, I think it was part of their presentation, a note that the cooling towers in the Yates building are below grade. And that does impact, of course, the condenser water temperatures, which is why they kind of skewed towards the VSS at that site. But of course, it's all site dependent. I know we had an attribution to the quietness of both chillers as people stood in the Yates mechanical room. Question for Dan and JJ. Is there any reliability data available on the VSS and the NBC chillers, given that they're both relatively new? We have a reliability data from the studies over a year, but is there anything beyond that that you're aware of?
This is Dan. I am not aware of that, but I can look and see what's available.
Okay. And then I think Juan can speak to at least the dependability of the NBCs. Juan, you've had those chillers installed for what, the last 3 to 4 years maybe in your region?
Yes, correct. Yes.
And operating pretty trouble-free?
To our knowledge, from talking with our operations group, we haven't encountered supposedly the lower condenser water temperature issues. Although, like I've been hearing that here at the regional level, it may be something I'll need to make sure I follow up down at the field level with the equipment specialists and UNM contractors that actually operate the equipment on a day-to-day basis to verify that and make sure that is the case. But we haven't come across like any major maintenance issues that I've been brought up on with the technology.
Hey Juan, this is Chris Sonseldu in McAllen. I can verify that we've got those smart D chillers in our area, and we haven't had any problems with them. And I think we got them installed in 2016. So
that's right.
As far as those go, we've been good. The ones that you know about in Brownsville.
Super. Thanks, Chris.
Great, thanks. Let's see. Julian asked, what is the expected equipment life for the VSS and NBC? Dan or JJ, I don't know if you can share any thoughts on that. I would imagine they're similar.
This is Dan. I have no reason to believe anything other than similar equipment lives.
Okay, thanks. And then Dan asks if the prices quoted were GSA price list quotes. I believe so. Those were market prices, right?
At the Yates building, the NBC chiller was purchased through normal channels, and the VSS chiller, because of the nature of the green proving ground, we were working with budget prices, but they were shopped third party as if it was being sold on a government contract, and the price that was listed in the report was confirmed.
And then Joshua asked, was the issue resolved to run multiple chillers at partial load rather than loading up a single chiller? In the case of the NBC, that's right. You stage your chillers so that the chillers operate kind of in their sweet spot. Julian asks, do you have sound data comparison that compares sound in the octave bands? And I will say that we don't have that as a part of our study. There might be somewhere out there in the marketplace, but not that I'm aware of. Does anyone know the cost associated with servicing the NBC versus the conventional chillers? I'm going to take that as NBC versus conventional centrifugal chillers. Does anyone, JJ, any thoughts on that?
Yeah, in the report, as I noted earlier, we didn't have any data on that. The only assumption that it would be lower because of the lack of oil requirements for that particular chiller.
Right. Let's see. Scott's got a question. JJ and Dan, I'll ask if you know. What is the max tonnage manufactured for the VSS and NBC, and how easy are they to get into the mechanical room? Are they modular? JJ or Dan, any thoughts on that?
I looked up, I was looking up the compressor manufacturer, and they're making up into the several hundred ton compressors now that can go on those chillers. So assuming they could operate them, install two compressors, and it's approaching 1,000 tons now.
I don't know, Juan, do you have any, Juan, can you off the top of your head state what the largest MBC is in your region?
The largest in our region for mag-bearing chillers is 750. I know that when I went to an energy conference in Atlanta, Smart was going to carry mag-bearing chillers, I think, up to 1,200 tons.
Okay,
as far as if they're the largest ones in the market, I'm not sure offhand, but that's the largest one I'm aware of.
Okay, thanks. Dan, any thoughts on the VSS? Do you know?
Yeah, the variable speed screw unit, when I saw this question, I just looked up their website real quick. Their largest unit is at 550 tons. And as far as the modularity goes, to get the units into the ACE mechanical room was a pretty impressive job of rigging.
Yeah.
They were ship modular. They were able to get them in place. And as far as I know, reassembly went well. Perhaps Glenn and Randy could address that in more detail since they were there every day.
Great, thanks. Shad asks, was a plate exchanger considered as a means to utilize low condenser water temperatures? I think that might be more of a Juan or a Kenny, your team question.
So the question was, did we consider looking at like flat plate heat exchangers?
It doesn't specify, but I would think. And if you don't know, that's fine. But
we've come across some cases where we had some. I think here in this building, here in the Lanham building, we have a flat plate heat exchanger, but we hadn't been using them. We hadn't been using it because of the mag-bearing chillers. In talking with Dana, in many cases, it seems like when we've installed these mag-bearing chillers, we've in places where we have flat plate heat exchangers, we've basically deactivated them because apparently the mag-bearing chillers are more energy efficient. Although I know the flat plate heat exchanger is beneficial in that it does provide free cooling in that sense. But apparently from talking internally with our operations group, they're more comfortable going with the mag-bearing chillers in places where we have flat plate heat exchangers.
Okay, thanks.
Mm-hmm.
Let's see. Opie asks, was there any independent oil and refrigerant analysis done after the same time energy frames or at the end of the test period? And I'm going to refer to our study, and maybe if you can just again talk about how we, did our best to operate side by side, day on, day off.
Yeah, to answer the specific questions, no, we did not do any oil or refrigerant analysis at the end of the test period.
Okay, thanks. I misread that. Let's see. Craig Campbell states that some MBC chillers can accept condenser water temps down to 36 degrees. So again, I think that's a design issue. Dan Foss-Dykenratz told us that, if you specify condenser water temps, they'll design to it. Let's see. Marty asked if you can get a copy of the slides. Andrea, I assume that's the case?
Yes, the copy of the slides will be posted on the GSA website, and as well as the recording of the presentation.
Okay. Let's see. I'm just going down looking at the questions. Dan asks, this is kind of out of scope a little bit, but let's give it a shot. Now, Dan asks, can you address free cooling selection there seems to be some interest in that. I don't know if JJ or Dan, you have any thoughts on free cooling when having these two chillers installed? Any thoughts on that, given that they operate well at the low load levels?
Yeah, this is Dan. Free cooling is very much a site-by-site item that has to be decided. Utility rate structures, dew points in the climate zones, there are myriad variables that go into that, and the discussion would be too complex for this case, for this discussion here.
Great, thanks. And then someone asked about the lower tonnage range for the VSS. Do you recall what you found was the lower limit?
I don't recall off the top of my head.
Okay, thanks. Jose Alvarez mentions that MBC chillers can unload to less than 5% based on the manufacturer design. Let's see. And then Gary states he believes the Train offers MBC as well. Zach asks, JJ, this is a question for you. The table of comparison between the, or no, maybe this is, sorry, Dan, for you. In the table of comparison between VSS and MBC, the coefficient of performance shows benefits of MBC at 100% and 25% loads. Is that for cooler weather states? How does that factor in for southern states?
This is Dan. When you're looking at that load profile, 100% down to 25%, that is based on a percentage of peak load. And peak load is not so much a trait of the climate zone that it's located in. Peak load and the amount of time that it spends at a part load is more of a factor of what is your building, how is it operating, is it a conventional office building that goes from empty on weekends to full in the summertime. So it's really, certainly climate is a part of what drives a decision when you're looking at a load profile, but also how the building operates.
Okay, great, thank you. Joe says the comparisons between VSS and MBC chillers. So are there chillers that are both VSS and MBC? And the answer is no. We had a VSS chiller and a separate MBC chiller, two different chillers in the Yates building. Let's see. Keith Sim makes the statement, the noise level given the presentation data table was in decibels, not octave band. We used decibel range, we didn't use octave band. So we didn't test frequency levels. I believe that's the case, right, Dan?
That is correct.
Is it? Okay. And let's see, someone asked the question, what happens if an MBC, if the power to the bearing fails, either by a power outage or electronic failure? And Jose answers, if there's a power failure, the MBC will coast down to a safe stop. Let's see. And Greg from Region 4 says that they've been installing MBCs for 8 years. So that's, a long time duration for dependability. They seem to be happy with them. Let's see. Bob Braun asked, are these chillers constant flow chillers, or can they adjust a variable flow chilled water and condenser water temperature flows?
I don't recall off the top of my head.
Okay, thanks. Josh asked if variable speed centrifugal has been considered for comparison, and the answer is no, not for these specific studies. Let's see. Let's see. Dana mentions maglev chillers can be bought with knockdown kits, so they can be shipped in similar, smaller components. So that confirms what Dan was saying. I think, Andrea, that's it for all the questions.
Okay, great. Thank you. Thank you, Mike. And if there are additional questions, feel free to reach out to us, and we'll see if we can get those answered. And as Mike said, attending this course is available for continuing education credit. After the completion, shortly you'll be receiving a very short 5-question survey, and by completing that survey, you'll receive continuing education credit. If you don't receive the survey for any reason, please reach out to Michael Hobson. His email is michael.hobson@gsa.gov, and he can get you set up with those continuing education credits. That should have been on the screen here. I'm going to show it here from a previous webinar, so you have that information of how to get the continuing education credits. And thanks very much for all of you for participating and for all the speakers. And again, we hope to see you at next month's webinar. Thank you.
Thank you.